There exists a planet so hostile that it pushes the very definition of what a world can be. Unlike the calm and life-bearing Earth, this place is drenched in fire, plagued by supersonic winds, and cursed with skies that shimmer with unnatural metallic clouds. Temperatures soar high enough to vaporize iron, while storms unleash molten rain across a landscape that never knows peace. Nothing here resembles safety, balance, or the possibility of life. Only chaos sculpted into a planetary form. This is the terrifying reality of WASP-189b. The true horror of this world begins not with the planet itself, but with the star it clings to in a deathly orbit. WASP-189b is bound to a massive A-type star known as HD 133112, a searing blue-white furnace that burns far hotter and brighter than our Sun. To put this into perspective, our Sun is classified as a G-type star, a middle-aged, relatively calm star that radiates just the right amount of heat and light to allow life to flourish on Earth. By contrast, an A-type star is a completely different beast, larger, more massive, and blisteringly hot, often shining several times brighter than the Sun. These stars are notorious for their intense ultraviolet radiation and violent stellar activity, producing conditions that make any nearby planets into cauldrons of chaos rather than havens for life. For WASP-189b, orbiting such a monster is not just an inconvenience, it is a death sentence, condemning it to eternal exposure under a relentless blaze that sculpts every aspect of its existence. The sheer radiance of HD 133112 bathes the planet in levels of heat and light that are almost unimaginable. A-type stars typically reach surface temperatures of around 7,500 to 10,000 degrees Celsius, compared to the Sun's relatively modest 5,500 degrees. This means WASP-189b's parent star radiates with a ferocity that pours vast amounts of energy into the planet's atmosphere every second. That energy doesn't just warm the planet, it destabilizes it, tearing apart molecules, stripping away normal gases, and leaving behind an atmosphere filled with exotic metallic vapors. Instead of clouds formed from water droplets, this hellish star's influence forces WASP-189b to form clouds of titanium oxide and vaporized iron, substances that would be lethal to humans in even the tiniest quantities. Every feature of this planet, from its blistering temperatures to its distorted shape, can be traced back to the merciless star it is trapped beside. What makes this relationship even more horrifying is the proximity. WASP-189b orbits so close to its star that it is practically skimming the stellar surface in cosmic terms. At such a close distance, the radiation and gravity from HD 133112 are overwhelming. The planet has no chance to form stable, Earth-like qualities. Instead, it is scorched, stretched, and bombarded endlessly. Astronomers often refer to planets in such orbits as hot Jupiters, gas giants that migrate perilously near their stars. But even among these infamous worlds, WASP-189b stands out as one of the most extreme. The star's energy is so overpowering that it locks one side of the planet permanently into daylight, a state known as tidal locking, ensuring that one hemisphere is roasted at all times, while the other is left in eternal darkness. The nightmare of WASP-189b begins with the star it orbits, and that star is nothing less than a celestial executioner. Another terrifying factor is how unforgiving A-type stars are when it comes to planetary survival. Unlike our Sun, which has a stable lifespan of around 10 billion years, A-type stars live fast and die young. Their lifetimes are typically only a fraction of that, often just 1 billion years or less, before they swell, collapse, or explode into something even more catastrophic. This means WASP 189b is locked in a race against time, clinging to its hostile star until the day it swells into a red giant or collapses in violent stellar death. For humans looking out at the cosmos, this is a sobering reminder. Planets like WASP 189b are not destined for long, stable existences, but instead are trapped in fleeting, violent lifespans governed by the fury of their parent stars. The universe does not always nurture, it often destroys, and this planet's fate is bound to its parent star's inevitable chaos. The discovery of WASP 189b's host star has also challenged astronomers because of its unusual characteristics. Most exoplanets discovered so far orbit stars similar to our Sun, but HD 133112 is one of the hottest and brightest stars ever found to host a planet. Studying it gives scientists a rare opportunity to see what happens to planets under the most extreme stellar conditions imaginable. The light from this star doesn't just illuminate the planet, it burns through it, altering its atmosphere and reshaping it into something alien. When astronomers observed WASP 189b using advanced instruments like the Cheops Space Telescope, they detected not only its incredible heat, but also the strange scattering of light in its atmosphere. That eerie blue glow, which makes the planet look otherworldly, is partly the result of how this monstrous star's light interacts with the planet's atmospheric chemicals. In essence, the very appearance of WASP 189b is painted by the unrelenting radiation of its host star. If there is one thing that makes this relationship especially chilling, it is the sheer helplessness of the planet. Unlike Earth, which orbits its star at a distance that allows oceans, clouds, and life to thrive, WASP 189b is trapped. There is no escape from its star's grip. The tidal forces are so strong that the planet's shape has been distorted, stretched into an oval rather than a sphere. It is almost as if the star is actively tearing the planet apart, reshaping it into something unnatural. This grotesque deformity serves as a physical reminder of just how merciless A-type stars can be to the worlds caught too close. What we see in WASP 189b is not a planet peacefully orbiting a star, but rather a victim shackled to a cosmic executioner, slowly being pulled, burned, and reshaped in ways that defy comprehension. Though this planet is one of the most hostile worlds ever discovered, it does not reside in some unreachable, unknowable corner of the cosmos. In fact, astronomers have pinpointed its location with remarkable precision. It lies about 322 light-years away from us, nestled within the constellation of Libra. To the naked eye, Libra is a familiar pattern of stars in our night sky, visible from many parts of Earth. Yet, hidden among its quiet lights is a system that harbors one of the most nightmarish planets known to science. The sheer distance is staggering. 322 light-years means that the light we see today from its star began its journey centuries ago, long before the rise of modern astronomy. By the time that light reached us, entire generations of human history had already unfolded. And yet, even across such a gulf of space and time, our instruments are sensitive enough to detect the faint signatures of this planet's existence. What makes this especially haunting is how close 322 light-years actually is on a cosmic scale. The Milky Way galaxy stretches over 100,000 light-years across, filled with billions of stars and countless planets, most of which are far beyond our current ability to study. Yet this planet sits just within our neighborhood, close enough for astronomers to not only detect its orbit, but also study its atmosphere. This proximity transforms it from an abstract curiosity into a tangible reality. It is not just a theoretical model or a distant speculation. It is a real world, burning in unimaginable heat that we can observe from our own tiny vantage point in the universe. The horror of this planet is magnified by that accessibility. It is not hidden on the far side of the galaxy. It is right there, a glowing beacon of chaos within reach of our telescopes. The constellation Libra itself adds another layer of eerie symbolism to this discovery. Libra, named after the scales of balance, represents harmony, justice, and equilibrium in ancient astronomy and mythology. To find a planet of such imbalance and horror lurking in a constellation tied to order and fairness is a cosmic irony. Where Libra's symbolism suggests stability, this planet represents the opposite. A world in permanent chaos, defined by extremes of heat and darkness, wind and fire, light and shadow. In many ways, it is as if the scales of Libra are being mocked by the existence of a planet that knows nothing of balance. Instead of harmony, it offers a portrait of destruction. From Earth, the light of this planet's host star is faint and unremarkable, blending into the backdrop of the night sky. To the casual stargazer, it appears like any other star, giving no hint of the inferno lurking in orbit around it. This is perhaps the most unsettling aspect. If we did not have the technology to study it, we would never know such a monstrous planet existed. It is a reminder that the universe hides its horrors well, disguising them behind the calm glow of ordinary starlight. Only through the ingenuity of modern science, using methods such as transit photometry and spectroscopy, have astronomers been able to peel back that disguise and reveal the terrifying reality of this world. The distance of 322 light-years also carries a sobering implication. It means that everything we observe about this planet is, in a sense, history. The light we detect today left the system 3 centuries ago. For all we know, the planet's environment may have shifted slightly in that time, though with conditions as extreme as these, it is unlikely that much has changed. Still, this time lag emphasizes how the universe forces us to peer into the past. Every glimpse of this planet is not a look at what it is now, but what it was when the light began its journey toward Earth. It is as though the cosmos teases us with a delayed reflection of its most nightmarish creations. And yet, despite this incredible distance, scientists have been able to study this planet's atmosphere directly. Few exoplanets allow for such detailed investigation, but this one is so massive, so close to its star, and so bright by comparison that its signals can be extracted with precision instruments. This allows astronomers to detect the strange chemical fingerprints of vaporized metals, the eerie scattering of light that produces its unsettling glow, and the violent conditions that dominate its skies. It is remarkable and terrifying that even across 322 light-years of space, we can know that this planet is a world of firestorms and metallic rain. For humanity, there is something chilling in realizing how close such a nightmare really is. While 322 light-years is beyond our reach for travel, it is still close enough to remind us that the galaxy is not a calm place filled only with Earth-like worlds and gentle stars. Instead, it is littered with extremes, with horrors beyond our imagination lurking just a few hundred light-years away. The universe does not need to stretch its full scale to terrify us. It can do so from right next door. This planet, burning in Libra, is proof of that reality. What makes this planet even more horrifying than its distance and its monstrous star is the sheer closeness of its orbit. Unlike Earth, which orbits the Sun at a safe and steady 150 million kilometers away, this planet circles its host star at a distance so small that it practically skims the stellar furnace. It belongs to a category of exoplanets known as hot Jupiters, gas giants similar in size or larger than Jupiter, but locked in orbits so tight that they defy the rules we once believed governed planetary systems. In our own solar system, Gas giants like Jupiter and Saturn exist far from the Sun, their distance providing stability and relative calm. But this world sits impossibly near its star, so near that its orbital period, the length of its year, is just 2.7 Earth days. Imagine an entire year compressed into less than a long weekend, with the planet completing its dizzying journey around its star in the blink of cosmic time. This closeness transforms the planet into a kind of living laboratory of extreme physics. The gravitational pull from the star is overwhelming, locking the planet in a tidal embrace that prevents it from spinning freely. As a result, one hemisphere of the planet forever faces the star, locked in perpetual daylight, while the opposite side is trapped in eternal darkness. This tidal locking creates a nightmare duality, an inferno on one side and a frozen abyss on the other, with unimaginably violent winds raging between the two extremes. The planet does not have the luxury of rotation to spread its heat evenly as Earth does. Instead, its existence is defined by imbalance, torn between fire and shadow. Orbiting this close to such a massive, scorching star also means that the planet is bombarded with radiation at levels we can barely comprehend. Earth's atmosphere shields us from the sun's most dangerous rays, but this planet has no such protection. The radiation saturates its skies, breaks apart molecules, and drives chemical reactions that produce exotic compounds unknown in Earth's atmosphere. The very air is toxic, metallic, and suffused with energy from the nearby stellar blaze. It is not simply hot, it is actively hostile, an environment that consumes rather than sustains. If one could stand on a hypothetical surface there, though such a surface doesn't exist, the exposure would be instant annihilation, a destruction brought about by the star's overwhelming proximity. Even the orbit itself speaks to the violent history of this world. Hot Jupiters are not believed to form so close to their stars. Instead, they are thought to have originated farther out, like Jupiter in our solar system, before migrating inward through chaotic gravitational interactions. That means this planet may once have been a more ordinary gas giant, only to be dragged inward, closer and closer to its star, until it settled into its current position of torment. It is, in a sense, a cosmic victim of its own system's gravitational dynamics, a giant planet forced into a suicidal orbit that guarantees its destruction. Over millions of years, the star's gravity and heat may strip away layers of its atmosphere, slowly eroding it until nothing remains. This planet is not just horrifying because of what it is. It is horrifying because it is doomed, trapped in a trajectory that will ultimately consume it. The speed at which it moves is another striking feature. With a year lasting just 2.7 Earth days, the planet races around its star at astonishing velocities. Its orbital speed is many times greater than Earth's, meaning it is constantly being whipped around by the immense gravitational pull of its host. This furious pace adds another layer of violence to its existence, amplifying tidal stresses and stretching the planet into an unnatural, elongated shape. The star's gravity does not simply hold the planet in place. It actively reshapes it, warping it into something grotesque. Unlike the calm, steady orbit of Earth, this planet's orbit is a relentless sprint around a cosmic furnace, a motion that embodies the very definition of instability. What makes this particularly unsettling is how common hot Jupiters actually are in our galaxy. Though our solar system has none, astronomers have found many orbiting distant stars, often among the first planets detected because their large sizes and close orbits make them easier to observe. This means that the kind of horrifying existence this planet endures is not rare. It is part of a broader category of worlds that defy our expectations. And yet, Even among hot Jupiters, this one is exceptional. Its proximity, combined with the nature of its host star, makes it one of the most extreme examples known to science. It is a reminder that planets do not always orbit in the comfortable zones we imagine. Sometimes, they are dragged so close to their stars that they become nightmares of fire and radiation. This planet's closeness to its star also changes how we think about planetary systems as a whole. It challenges our assumptions about where gas giants can exist and how they evolve over time. The discovery of hot Jupiters was one of the first great surprises of exoplanet science, shaking the foundations of planetary formation theory. This planet, with its blistering orbit of just 2.7 days, continues to be a case study in that mystery. How could a giant planet survive in such conditions? How long can it endure before it is stripped apart? And what does its existence say about the diversity and danger of planetary systems throughout the cosmos? For us, this proximity translates into one chilling conclusion. The universe is capable of producing worlds that live permanently in the shadow of annihilation. This planet's orbit is not a safe distance like Earth's, nor is it a distant frozen expanse like Neptune's. It is a thin balance between existence and destruction, circling so close to its star that survival is little more than a temporary illusion. Every orbit is a reminder of its fate, every 2.7-day year a testament to its imprisonment. It is a planet too close to its star, too close to safety, and too close to the edge of destruction to ever know peace. The most horrifying feature of this planet is its staggering heat. Locked in a suffocatingly close orbit around its blue-white star, it is constantly scorched by radiation so intense that its atmosphere is transformed into a fiery cauldron. Temperatures on the day side soar to around 3,200 degrees Celsius, or nearly 5,800 degrees Fahrenheit. To put that into perspective, this is hotter than molten lava, hotter than the surface of most known rocky planets, and astonishingly, even hotter than some low-mass stars known as red dwarfs. At such extreme levels of heat, the concept of surface becomes meaningless. Any solid material would vaporize instantly, metals melt into gases, and molecules are ripped apart before they can even form bonds. This is not a world of oceans, mountains, or plains. It is a world where the very building blocks of matter are constantly being torn asunder by heat that defies imagination. What is especially unsettling is that 3,200 degrees Celsius is not just a number. It is a regime of physics that fundamentally changes how a planet behaves. On Earth, high temperatures mean deserts, volcanoes, and wildfires. On this planet, they mean an entire atmosphere made of vaporized metals, iron clouds suspended like toxic mists, and molecules like titanium oxide floating high in the skies. The heat is so overwhelming that even atoms are energized beyond what we normally consider stable. Ordinary chemistry is obliterated. Water, the essential liquid for life as we know it, could not possibly exist here in any form, not as ice, not as liquid, not even as vapor. The planet is so hot that it moves into a realm of exotic atmospheres, alien environments where only strange and deadly substances can survive. What makes this even more terrifying is the permanence of the heat. This is not a temporary flare-up like a volcanic eruption or a brief solar storm. This planet exists in a perpetual inferno. Because it is tidally locked, one side of the planet always faces the star. That hemisphere is endlessly scorched, never given a moment of respite from the unrelenting blaze. Day never ends, and night never comes. The atmosphere there is a constant storm of burning gases, whipped into motion by winds that try in vain to redistribute the heat to the other side of the planet. Even the night side, though shielded from direct starlight, is anything but calm. The winds carry searing gases across the globe, ensuring that the planet as a whole remains blisteringly hostile. In this sense, the heat is not just a feature, it is the entire identity of the planet. It is worth pausing to consider how rare and horrifying this level of heat really is. In astronomy, stars are classified by their temperatures, and while most stars are hotter than planets, this world sits in a grey area. At over 3,000 degrees Celsius, it rivals the cooler members of the stellar family, making it a planet that behaves more like a star. Some astronomers even describe planets like this as failed stars, because they burn so fiercely that they blur the line between planet and star. It is as though nature itself is confused about what this object should be. For observers on Earth, this is what makes it truly nightmarish. It is not just a planet gone wrong, but a planet that masquerades as something else, straddling the boundary between worlds and suns. The blistering temperatures also have profound effects on the physics of the planet's atmosphere. At 3,200 degrees Celsius, the gases in the atmosphere expand and rise, creating massive circulation currents that feed into supersonic winds. These winds attempt to shuttle heat from the permanent day side to the eternal night side, creating storms unlike anything in the solar system. While Earth's strongest hurricanes and cyclones seem devastating to us, they are nothing compared to the planet-wide storms driven by temperatures that melt metal. In a sense, the planet's own atmosphere is in constant rebellion, trying and failing to cope with the unimaginable energy pouring in from its nearby star. The result is a dynamic system of chaos, where fire and wind are locked in an endless battle that ensures the planet never knows peace. One of the most sobering aspects of this environment is its sheer hostility to life. Not just life as we know it, but life in any conceivable form. At 3,200 degrees Celsius, even the most durable extremophiles on Earth, organisms that thrive in the boiling waters of volcanic vents or in the frozen extremes of Antarctica, would be instantly annihilated. Organic molecules themselves cannot survive here. Carbon-based chemistry breaks down, proteins unravel, and DNA disintegrates in the face of the planet's fiery onslaught. This planet is not merely uninhabitable, it is fundamentally incompatible with the processes that sustain life anywhere in the universe. Its heat acts as a cosmic firewall, erasing even the possibility of survival. Astronomers have studied this heat with awe because it provides a window into conditions rarely observed in the universe. By measuring the light emitted and reflected by the planet, scientists can detect the chemical fingerprints of its scorching atmosphere. The very fact that we can measure a temperature so extreme on a planet so distant is a testament to human ingenuity. But those measurements come with a chilling realization. This is one of the hottest exoplanets ever discovered, an outlier among outliers. A world where the thermometer never drops low enough for comfort, not even by a fraction. Every second of its existence is defined by fire, its very identity forged in heat. For humanity, these blistering temperatures serve as a reminder of how fragile Earth's balance really is. Our planet exists in a narrow habitable zone where liquid water can exist, where temperatures allow life to thrive, and where the atmosphere shelters us from the extremes of space. Move a little closer to the Sun, and Earth would risk a runaway greenhouse effect, like Venus. Move much farther away, and Earth would be plunged into ice. This planet shows us what happens when the balance is lost completely. A world consumed by fire, destroyed by its own proximity to its star, and locked forever in an inferno that makes even stars seem mild by comparison. It is the cosmic embodiment of heat and destruction, a blazing horror adrift in the constellation Libra. The hellish nature of this planet is made even more surreal by the strange and haunting blue glow that emanates from it. While the extreme heat and metallic storms make it terrifying in theory, It is this eerie luminescence that gives it an otherworldly presence, almost as if the planet itself is alive with a cold, spectral fire. Astronomers have observed this phenomenon through precise measurements of the planet's reflected and emitted light, noting that the atmosphere scatters starlight in unusual ways that produce the unsettling blue coloration. Unlike the warm oranges and reds we often associate with hot planets or molten surfaces, this chilling azure light gives the planet an alien aura, a stark reminder that it does not conform to anything we recognize in our solar system. The glow is not merely decorative, it is a visible marker of the planet's extreme conditions, a visual signature of the violent physics at work in its atmosphere. The reason behind this ghostly blue glow lies in the composition and behavior of the planet's atmosphere. Layers of vaporized metals, such as titanium and iron, combine with exotic chemical compounds to create a medium that interacts with light in strange and unpredictable ways. When the intense radiation from its star strikes the planet, photons are scattered, absorbed, and re-emitted in a manner that favors shorter wavelengths, producing that haunting blue hue. This scattering is similar in concept to why Earth's sky appears blue, but on a scale and intensity that is far beyond anything found on our own planet. On Earth, Rayleigh scattering diffuses sunlight gently through nitrogen and oxygen. On this planet, the same basic principle is amplified by the presence of metal-rich clouds and the searing energy pouring in from the nearby star, resulting in an alien shimmer that seems almost supernatural. From a distance, this glow would make the planet appear like a spectral orb, hovering in the void, with a color that is both beautiful and deeply unsettling. It is the kind of phenomenon that draws the eye and unsettles the mind simultaneously, producing a visual contradiction, something that appears almost mesmerizing, but is, in reality, a world of unrelenting violence and heat. The glow also hints at the internal dynamics of the planet, signaling where intense thermal energy interacts with the atmospheric composition. Each photon escaping from the upper layers of the atmosphere carries information about temperature, wind, and chemical composition, effectively allowing astronomers to see the planet's conditions from hundreds of light years away. In this sense, the eerie blue glow is not just an aesthetic feature, it is a diagnostic tool, a cosmic fingerprint revealing the horrors taking place beneath its shimmering surface. The haunting beauty of this color also contrasts sharply with the planet's violent physical environment. While humans might perceive blue as calming or peaceful, here it is a warning. It marks a place where metals rain down from the sky in molten droplets, where supersonic winds roar across the day and night sides, and where no known form of life could survive. The glow becomes a symbol of the planet's alien nature, a visual representation of the extreme separation from any world we would consider hospitable. Unlike the sun's gentle yellow warmth or the red embers of a distant gas giant, this planet emits a spectral blue that evokes both fascination and dread. It is as if the planet is wearing a mask of beauty to disguise its terrifying reality, a cosmic siren calling scientists to study it, while simultaneously reminding them of its lethal nature. Interestingly, this phenomenon also challenges our understanding of planetary atmospheres. Most exoplanets studied in detail have shown either reflective cloud layers or simple thermal emissions that are easy to interpret. This planet, however, demonstrates a level of complexity that is both intriguing and alarming. The scattering of light in such extreme conditions forces scientists to refine their models, considering how vaporized metals, supersonic winds, and tidal forces interact with high-energy radiation. Each of these factors contributes to the blue glow, creating a layered, dynamic atmospheric system that is constantly in flux. Observing it is like watching a living chemical experiment on a planetary scale, one driven by forces so powerful that they exceed anything experienced on Earth. The glow is also critical in the way it allows astronomers to study the planet directly. Unlike most exoplanets, which are detected indirectly by the dimming of their host stars, this planet's atmosphere is bright enough in certain wavelengths to be analyzed through spectroscopy. The haunting blue light carries with it signatures of the atmospheric chemistry, allowing scientists to determine the presence of metals like titanium and iron, and to infer the intensity of the heat and winds across its surface. This makes it one of the few exoplanets whose environmental conditions can be observed in such vivid detail, providing a rare glimpse into the workings of a world so extreme that it seems almost unreal. Ultimately, the eerie blue glow of this planet serves as both an invitation and a warning. It draws our attention across hundreds of light years, captivating astronomers and enthusiasts alike, but it also signals the relentless hostility of the environment beneath. It is a world of contradictions, beautiful yet deadly, glowing yet scorched, alien yet chemically understandable. The glow is a reminder that in the universe, danger often wears a mask of wonder, and that even in beauty, there can be an underlying terror. It is this spectral signature, this haunting color, that first makes the planet unforgettable, a luminous monument to cosmic extremes, a beacon of both scientific curiosity and existential dread. The terrifying nature of this planet is further amplified by the phenomenon of tidal locking, a brutal consequence of its extreme proximity to its star. Unlike Earth, which rotates freely and experiences a regular cycle of day and night, this planet is gravitationally tethered so tightly to its star that one hemisphere is permanently locked toward the relentless blaze above. This means that one side experiences eternal daylight, a constant, unending bombardment of heat and radiation, while the opposite side languishes in perpetual darkness, never receiving a single ray of stellar light. The result is a planet split in two extremes, a world of fire on one side and frozen shadow on the other, with no transition or reprieve in between. This eternal division magnifies every other horror. The scorching temperatures, the supersonic winds, the molten metal clouds, all are intensified by this immutable imbalance. On the side facing the star, the planet is a furnace beyond comprehension. Temperatures reach the staggering 3,200 degrees Celsius measured by astronomers, enough to vaporize metals and create an atmosphere filled with exotic poisonous gases. Day never ends here. Unlike Earth, which can recover or cool during the night, this hemisphere endures an unbroken onslaught of radiation, baking its clouds of titanium and iron into a roiling, searing maelstrom. Storms rage continuously, fueled by the constant energy input, whipping the atmosphere into supersonic winds that transport scorching gases from the day side toward the night side. It is an environment where stability is impossible, where every moment is a battle against the star's relentless fury. Meanwhile, the dark hemisphere is no sanctuary. Deprived entirely of the star's energy, temperatures plummet to levels that are equally extreme in their own right. The eternal night is frigid, with gases condensing as the metallic vapors transported by the winds from the dayside collide with the cold. Iron and titanium droplets might rain down here as molten metal, freezing upon hitting colder layers of the atmosphere, creating a bizarre, fiery precipitation that is alien and hostile. Winds from the dayside slam into the dark hemisphere at thousands of kilometers per hour, driven by the imbalance between the hemispheres, creating storms that are as violent as they are unpredictable. Even in darkness, there is no calm. The night is a frozen battlefield, lit only by the faint glow of escaping photons and the spectral shimmer of the planet's unusual atmospheric composition. The boundary between eternal day and endless night, known as the terminator line, is one of the most fascinating and terrifying regions on this planet. Here, the temperatures begin to shift, metals start to condense from vapor, and winds from the day side clash with the cold air of the night side. It is a place of extreme turbulence, where the physical and chemical dynamics of the planet reach a chaotic crescendo. Clouds of molten metal, carried by supersonic gusts, swirl in intricate patterns, and lightning-like phenomena may arise as charged particles interact violently. Scientists studying the planet describe this region as a literal battlefield between light and shadow, a zone where the physics of extreme atmospheres are pushed to their limits. Tidal locking also has profound implications for the structure and evolution of the planet. The continuous gravitational pull from the star not only fixes the planet's rotation, but also stretches its shape into a slightly elongated oval form, further amplifying the instability of its environment. Unlike planets like Earth, which have the luxury of rotation to distribute heat and maintain relative equilibrium, this planet cannot moderate the extremes. Its climate, weather, and atmospheric dynamics are all dictated by the inescapable division of eternal day and night. It is as though nature itself has forced the planet into a permanent state of imbalance, a living experiment in extremes that could never occur in a more benign environment. The psychological implications of such a world are equally haunting. To imagine standing on a hypothetical surface, or rather drifting within its atmosphere, is to imagine a place where the concept of time itself is alien. There is no sunrise, no sunset, no cycle to mark hours or days. One side is unrelenting fire, the other unending darkness, and the transition between them is violent and unwelcoming. This eternal duality forces a reconsideration of everything we think we know about planetary environments. Life, as we understand it, thrives on cycles, on change, on the rhythm of day and night. Here, no such rhythm exists. The planet is locked in a perpetual struggle, a stark reminder that the universe is capable of extremes far beyond human experience. From an observational standpoint, tidal locking also provides scientists with unique opportunities to study the planet. By examining the differences between the day and night sides, astronomers can measure how heat is transported, how atmospheric chemicals react under extreme conditions, and how winds behave under near impossible stress. These studies reveal that the planet is not merely hot, it is dynamic, violent, and extraordinarily complex, with permanent light and shadow, driving storms, chemical reactions, and atmospheric circulation in ways rarely observed anywhere else in the cosmos. The very fact that one side is locked in fire while the other is locked in shadow makes it a natural laboratory for extreme planetary physics. The horror of this planet becomes even more tangible when considering what its atmosphere is made of. Unlike Earth, where clouds are composed of water vapor and precipitation is gentle rain, this planet's skies are a furnace filled with vaporized metals. The blistering temperatures, driven by relentless radiation from its nearby star, are sufficient to vaporize elements such as iron and titanium, converting them from solid or liquid forms into gas. Instead of drifting fluffy clouds of water vapor, the atmosphere is dominated by dense metallic gases that swirl across the planet in waves of heat and energy. Iron, which on Earth forms solid rock or rust, rises here into the sky as a glowing molten vapor. Titanium, one of the strongest and most resilient metals we know, behaves in a similar fashion, becoming part of an infernal sky that is alien in composition and deadly by nature. These metallic clouds are not just a curiosity, they are a manifestation of the extreme environmental stress imposed by the planet's proximity to its star. The presence of vaporized metals dramatically alters the planet's chemistry and appearance. On Earth, clouds reflect sunlight, scatter heat, and can moderate weather. On this planet, the metallic clouds act in entirely different ways. Titanium oxide, one of the primary constituents of the atmosphere, interacts with the intense starlight, absorbing and scattering energy in ways that amplify both heat and the eerie blue glow observed from afar. Iron vapor, meanwhile, contributes to a strange metallic sheen across the atmosphere, producing visual effects unlike any sky we know. The clouds are not gentle or benign. They are dense, heavy with energy, and capable of conducting heat across the planet's hemispheres. Instead of providing relief from the searing temperatures, they perpetuate the inferno, transporting vaporized metals from the day side toward the night side and fueling violent storms along the terminator line. This metal-rich atmosphere also challenges our understanding of how gases behave under extreme conditions. On Earth, water vapor condenses into droplets, forming precipitation. But here, iron and titanium behave differently due to the intense heat and pressures. As vaporized metals rise and cool slightly, they may condense into droplets of molten metal, creating precipitation that is literally fiery. Clouds are no longer soft, fluffy structures. They are immense, roiling factories of molten chemistry, suspended in a sky where no air is breathable, no moisture is benign, and no environment is safe. Scientists studying the planet are fascinated by this extreme chemistry because it demonstrates atmospheric processes operating in regimes far beyond what we see in our solar system. The planet essentially turns metals into clouds, precipitation, and storms, creating a full meteorological cycle made entirely of elements that on Earth would be considered rigid, inert, or durable. One of the most haunting aspects of these metallic clouds is their movement. Driven by supersonic winds and extreme temperature gradients between the day and night sides, the vaporized metals do not remain still. Iron and titanium vapor can travel thousands of kilometers across the planet, moving from the endlessly blazing day side to the frozen night side. During this journey, the gases cool just enough to begin condensing, forming clouds that swirl violently and create a perpetual storm system. Lightning-like discharges may even occur as these charged metallic clouds interact with one another, producing phenomena that are almost incomprehensible to anyone accustomed to terrestrial weather. The planet is not simply hot. It is alive with violent, dynamic processes in which molten metal is the primary agent, replacing the life-giving water cycles we are familiar with. The extreme heat and metallic composition of the atmosphere also have consequences for the planet's overall structure. As metals vaporize and condense, they carry tremendous amounts of energy, redistributing heat across the globe and influencing the dynamics of its violent winds. The result is a self-reinforcing cycle of destruction. Heat vaporizes metals. Vaporized metals form clouds. Clouds move under violent winds, and winds transport heat to other parts of the planet, maintaining or even amplifying the already extreme conditions. Unlike Earth's relatively balanced weather systems, this planet's climate is chaotic, unrelenting, and lethal, governed by physics at the limits of possibility. It is a world where ordinary rules of planetary atmospheres do not apply, where metals rise and fall as clouds, and where survival of any kind is impossible. From a visual standpoint, these metallic clouds are as striking as they are terrifying. The vaporized iron can shimmer with a faint reddish hue under the star's intense light, while titanium oxide contributes to the ghostly blue glow that gives the planet its otherworldly appearance. Together, they create a sky that is both mesmerizing and horrifying, a ceaseless storm of glowing metals that drift, condense, and rain in a cycle that no human eye could safely witness. The planet's skies are therefore not just hot and violent. They are literally composed of materials that are foreign to any known life-supporting environment, a constant reminder that this is a world entirely alien and inhospitable. The presence of vaporized metals also underscores the utter impossibility of life here. Even the hardiest organisms we know could not survive exposure to metallic vapors heated to thousands of degrees. DNA, proteins, and organic molecules would disintegrate instantly, ensuring that this planet remains forever sterile. Water-based life, the kind we understand and rely upon, is entirely absent, not merely rare, but physically impossible under these conditions. The clouds of iron and titanium, once solid elements on Earth, become a medium of destruction, shaping the planet into a furnace where chemistry itself is weaponized. In every way, the metallic atmosphere of this planet reinforces its status as one of the most horrifying worlds ever discovered. Clouds of vaporized iron and titanium replace familiar water cycles. Storms carry molten droplets across endless landscapes. And the interaction of these metals with extreme heat and wind creates a planet-wide system of perpetual chaos. It is a realm where the very elements themselves have been repurposed into agents of destruction. A planet that demonstrates the extremes of what a world can become when pushed beyond the boundaries of Earth-like physics. Here, the air is lethal, the sky is fire, and the clouds themselves are instruments of terror. The already nightmarish atmosphere of this planet becomes even more terrifying when considering the phenomenon of metal rain. With temperatures so high that elements like iron and titanium exist in vapor form, the atmosphere is a seething ocean of molten metals suspended in gas. But as these vaporized metals are transported by the planet's violent winds toward cooler regions, particularly along the terminator line where day meets night, they begin to condense. What emerges from this process is an unimaginable spectacle. Droplets of molten iron and titanium raining down from the sky. A literal storm of fire and metal that has no equivalent anywhere on Earth. This is not rainfall as we know it, where water nourishes life and replenishes rivers and lakes. This is precipitation that would instantly obliterate anything it touched. A metallic downpour hotter than the surface of most stars. The mechanics of this metal rain are as extraordinary as they are horrifying. The extreme winds that sweep across the planet at thousands of kilometers per hour carry vaporized metals from the blazing day side to the frigid night side. During this journey, the gases cool slightly and the metals condense into molten droplets. Unlike water droplets, which are relatively light and slow, these metal droplets are dense, heavy, and blisteringly hot. As they fall, they likely fuse into streaks of incandescent metal, sizzling and vaporizing even as they descend, creating a storm of kinetic energy and heat, unlike any atmospheric phenomenon on Earth. The skies would appear to boil, molten droplets arcing across turbulent clouds, illuminated by the eerie blue glow of the atmosphere. This is a planet where precipitation is a weapon, where the weather itself is a relentless, fiery assault. The consequences of such metal rain are terrifying on a planetary scale. The droplets would continuously strike the upper layers of the atmosphere, vaporizing upon contact, but adding energy back into the already searing skies. This constant cycle of vaporization and condensation contributes to supersonic winds, violent storms, and a turbulent, almost living atmosphere. The rain is not uniform. It is chaotic, unpredictable, and unending, fed by the immense energy input from the nearby star. In effect, the planet is perpetually self-destructing and regenerating, a ceaseless cycle of metal vapor and molten precipitation that ensures no region is ever calm or safe. It is a storm system so extreme that it challenges our very understanding of planetary atmospheres, operating in a regime of physics that Earth-based meteorology cannot replicate. The metallic precipitation also interacts with the strange chemical composition of the atmosphere, enhancing the alien appearance of the planet. molten titanium droplets may refract light in peculiar ways, contributing to the eerie blue glow observed by astronomers, while vaporized iron may create a faint reddish shimmer in the dense clouds. The result is not only a storm of destruction, but a visual spectacle of horrifying beauty. A sky that glows, burns, and rains molten metal all at once. It is simultaneously mesmerizing and terrifying, an aesthetic that humans might describe as apocalyptic, a vision more at home in a nightmare than reality. From a scientific perspective, this metal rain is an extraordinary case study. It demonstrates how elements behave under conditions of extreme heat and pressure, offering insights into planetary atmospheres far beyond anything found in our solar system. Iron and titanium, metals that on Earth are rigid and durable, are transformed into active agents of the weather, carried by winds, vaporized, condensed, and rained down in a continuous, planet-wide storm. The energy involved in this process is staggering. Every droplet of molten metal represents not just mass, but the conversion of heat into motion, kinetic energy, and light, an entire hydrological cycle of fire and destruction. It is a vivid demonstration of how extreme environments can reshape the very laws of physics as we understand them on Earth. Perhaps the most horrifying aspect of this metal rain is its permanence. Unlike storms on Earth, which eventually dissipate, these metallic downpours are a constant, unending feature of the planet's climate. The day side relentlessly vaporizes metals, winds transport them, and the night side serves as the condensation zone, creating a ceaseless cycle. There is no reprieve, no pause, no calm before the storm. The planet exists in a state of eternal meteorological chaos, where every moment is defined by fire, heat, and molten precipitation. Even if hypothetical observers could endure the heat and radiation, they would witness a world in continuous, destructive motion, where the sky itself is a deadly weapon raining molten metal from horizon to horizon. In essence, this metal rain is a manifestation of the planet's extreme identity. It transforms atmospheric chemistry into a mechanism of violence, creating conditions that are both scientifically fascinating and profoundly terrifying. It reminds us that not all planets are gentle spheres of rock or gas. Some are active, dynamic, and utterly inhospitable, turning the elements themselves into instruments of destruction. On this planet, there are no clouds of water, no nourishing rain, no cycles of life, only molten metals falling in a storm that exemplifies the sheer scale of cosmic extremes, a world where even the act of precipitation is lethal. The chaos of this planet is made even more extreme by the sheer ferocity of its winds. Supersonic gusts, traveling at thousands of kilometers per hour, tear across the atmosphere, driven by the enormous temperature differences between the eternal day side and the perpetual night side. On Earth, the strongest hurricanes reach speeds of around 300 kilometers per hour, devastating enough to wreak havoc on cities and landscapes. But on this planet, these supersonic winds dwarf anything experienced in our solar system, carrying searing, vaporized metals across the globe in a relentless, unyielding torrent. These winds are not merely air currents, they are conveyors of destruction, transporting molten iron, titanium, and other metallic vapors from the endlessly scorching hemisphere to the frigid night side, perpetuating a cycle of violent storms and metallic rain that knows no respite. The winds are a direct consequence of the planet's tidal locking and extreme heat. On the day side, the atmosphere is superheated by the constant radiation from the star, creating a massive pressure gradient between the scorching hemisphere and the frozen night side. Nature, in its relentless drive to balance extremes, pushes this heated air across the planet at velocities beyond imagination. As the superheated gases surge toward the night side, they cool rapidly, carrying metals that condense into molten droplets and rain down in fiery storms. This movement of matter is not gradual, it is violent, chaotic, and continuous, a global atmospheric conveyor belt of heat, energy, and destruction. It is a process that transforms the entire planet into a living, breathing system of fire and metal. These supersonic winds also serve to mix the atmosphere in ways that are both fascinating and terrifying. On Earth, atmospheric mixing helps distribute heat, water, and energy, sustaining a relatively stable climate. On this planet, however, the winds amplify instability. They collide with themselves, whip around the terminator line between day and night, and create turbulence so extreme that clouds of vaporized metals swirl into chaotic vortices. Lightning-like discharges may form as charged metallic particles interact violently, producing localized bursts of energy that add another layer of danger to an already inhospitable environment. The atmosphere is, in effect, a perpetual storm machine, with the supersonic winds acting as its driving engine, never resting, never slowing, and never allowing the planet to settle into calm or equilibrium. Another horrifying aspect is the role these winds play in shaping the planet's visual appearance. As molten metals and exotic gases are transported across the globe, they reflect and scatter light from the nearby star, contributing to the eerie blue glow that makes the planet so visually alien. The movement of the metallic clouds under supersonic winds creates a dynamic, almost living visual spectacle. Roiling clouds, streaks of molten metal, and flashes of energy that illuminate the planet in an ever-changing dance of light and shadow. From a distance, this gives the planet a haunting, almost ethereal appearance, but anyone approaching it would find that this beauty conceals unimaginable violence. The winds are not merely an aesthetic feature, they are a lethal force, shaping the distribution of heat, metals, and energy across the planet. The intensity and permanence of these winds also have profound implications for the planet's physical and chemical systems. They continually move metals from the day side to the night side, where they condense and fall as molten precipitation, only to be reheated and vaporized again as they return to the day side. This creates a ceaseless cycle of destruction, with energy and matter constantly being redistributed in a way that reinforces the planet's extreme conditions. Unlike Earth, where storms are temporary and localized, these winds operate on a planetary scale, ensuring that no corner of the globe is free from chaos. Every second, every gust, every metal droplet is part of an ongoing, violent system that defines the very nature of this alien world. Scientifically, these supersonic winds provide a unique window into atmospheric physics under extreme conditions. They demonstrate how heat transfer, fluid dynamics, and chemical interactions operate when pushed far beyond the limits seen on Earth or even in most known exoplanets. By studying the behavior of these winds and their effects on the metallic atmosphere, astronomers gain unprecedented insight into how planets respond to extreme heating, rapid rotation, or in this case tidal locking, and intense stellar radiation. It is a natural experiment conducted on a scale and under conditions that human laboratories could never replicate, revealing the destructive power inherent in the universe when a planet is forced into such an unforgiving orbit. Ultimately, the supersonic winds of this planet are a defining feature of its horror. They are the invisible hands that move the molten metals, the agents of its eternal storms, and the conveyors of unrelenting chaos. They ensure that the planet remains in a constant state of upheaval, where no region is ever safe and no process ever slows. These winds are not just a meteorological phenomenon. They are an expression of the planet's extreme nature, a tangible reminder that in the cosmos, violence can be global, continuous, and unimaginably intense. On this planet, the very air is alive with fury, and the winds themselves are a force that shapes a world of fire, metal, and eternal destruction. The immense scale of this planet adds another layer to its terrifying nature. Measuring roughly 1.6 times the size of Jupiter, it is not only enormous compared to Earth, but also significantly larger than the largest planets in our own solar system. To visualize this, imagine a world that could fit more than 1,000 Earths within its volume, a true giant drifting through space. Its size alone would make it a commanding presence in any star system, but coupled with its extreme environment, this is not a benevolent giant. Rather, it is a monstrous, hellish world whose sheer dimensions amplify every aspect of its hostility, from its blistering temperatures and supersonic winds to its metallic clouds and fiery rains. A larger planet has more gravitational energy, more atmospheric mass, and greater capacity to sustain the violent cycles of heat and storm that define it, making it an unrelenting, self-perpetuating furnace on a scale that boggles the imagination. The size of this planet has profound consequences for its atmosphere and weather systems. A world this massive can retain incredibly dense layers of gas, allowing vaporized metals such as iron and titanium to accumulate and persist in the skies rather than escaping into space. This enhances the intensity of the metallic clouds, creating storms that span thousands of kilometers, dwarfing even the largest hurricanes or cyclones ever observed on Earth. Supersonic winds sweeping across its enormous surface can reach higher velocities, and the planet-wide circulation patterns become more extreme as the energy from the scorching day side is transferred to the night side. Essentially, the greater the size, the more massive and unrelenting the storms, the stronger the winds, and the more catastrophic the metal rain, producing a planetary-scale system of perpetual chaos. Moreover, its giant size interacts with the intense gravitational pull of its nearby star, further exacerbating its deformities. The planet is not a perfect sphere. Tidal forces stretch it into an oval, elongating it along the axis, pointing toward its star. This deformation, combined with the massive gravitational energy of such a large planet, intensifies the instability in its atmosphere. Wind patterns, storms, and precipitation are all affected by this distortion, creating unpredictable turbulence and making its already violent environment even more extreme. Imagine a storm system on Earth, amplified not just by heat and pressure, but by the very shape of the planet itself being contorted by a star's gravity. This is the reality on this colossal, tortured world. The sheer size of the planet also magnifies its visual impact from afar. Its radius and volume allow it to intercept and re-radiate enormous amounts of starlight, contributing to the eerie glow that makes it so visually distinct. The combination of metallic clouds, vaporized elements, and the reflective properties of molten metals is intensified by the planet's scale, producing a luminous spectacle that is both mesmerizing and horrifying. Observations reveal not just the size, but the dynamic processes occurring across a vast, unrelenting surface. This is not a small, isolated hell. It is a sprawling inferno, stretching thousands of kilometers in every direction, with every square kilometer contributing to the planet's hostile identity. Even its mass plays a role in its nightmarish qualities. With a volume 1.6 times that of Jupiter, the gravitational pull on the planet is tremendous, shaping the behavior of its atmosphere, influencing wind speeds and affecting the dynamics of metallic precipitation. The denser atmosphere helps trap heat and allows the violent supersonic winds to transport metals over incredible distances. In effect, the larger the planet, the more capable it is of sustaining these extreme processes on a global scale. While smaller exoplanets may experience temporary heat spikes or storms, a giant like this can maintain an inferno continuously, with its massive gravity and atmosphere acting as a catalyst for perpetual chaos. Its colossal size contrasts sharply with any notion of habitability. Even if we were to somehow endure the blistering heat, supersonic winds, and metallic rain, the sheer scale of the planet makes it impossible to navigate or survive in any practical sense. There is no surface safe enough to stand on, no sheltered areas to escape the storms, no regions of calm amidst the chaos. The size amplifies everything terrifying about the planet: its heat, its storms, its metal-rich atmosphere, turning it into a fully realized, planetary-scale nightmare. In short, this is not just a planet that is big, it is a world where magnitude itself contributes to its horror, where every kilometer of surface is an arena of extreme physics and unrelenting violence. The atmosphere of this planet elevates its terror to levels that are almost incomprehensible. Unlike the familiar nitrogen-oxygen mixture of Earth, this planet's skies are dominated by exotic chemicals that behave in ways entirely alien to our experience. Titanium oxide is one of the primary constituents, a substance that, on Earth, is used in paint and sunscreen, reflecting and scattering sunlight. But on this planet, titanium oxide and other exotic chemicals operate on a massive, almost weaponized scale. They interact with the searing radiation from the nearby star, absorbing, reflecting, and redistributing heat in ways that both amplify and redirect the infernal energy. This creates pockets of the atmosphere that are simultaneously hotter than molten lava and chemically charged with elements that would obliterate any organic material, making the air itself a lethal barrier to life. These chemicals, in combination with the planet's vaporized metals, produce a climate that is not just hot, but dynamically hostile. Titanium oxide, for instance, can absorb stellar radiation and re-emit it unevenly, trapping heat in the atmosphere and contributing to massive thermal gradients between the day side and night side. This is similar in principle to ozone on Earth, which protects us by absorbing ultraviolet radiation. But the scale and intensity here are orders of magnitude beyond anything terrestrial. The result is a sky that is chemically reactive, constantly in flux, and capable of sustaining violent storms that transport molten metals at supersonic speeds. Unlike Earth, where the atmosphere often acts as a buffer or regulator, here it is an active participant in the planet's extreme hostility, amplifying every destructive process rather than mitigating it. The chemical composition also contributes to the planet's eerie visual characteristics. Titanium oxide particles in the upper atmosphere scatter shorter wavelengths of light, creating the ghostly blue glow that is visible even across hundreds of light years. Iron and other vaporized metals further contribute to the shimmer, producing a sky that seems simultaneously luminous and deadly. Clouds of these chemicals swirl in constant motion, twisted by supersonic winds, forming turbulent metallic-streaked patterns that are as mesmerizing as they are terrifying. This is an environment where beauty and danger are inseparable, where even the act of observing the skies would expose a hypothetical visitor to lethal radiation and extreme heat. Beyond the visual and thermal effects, the exotic atmosphere also drives complex chemical reactions on a scale that would be unimaginable on Earth. High-energy radiation from the star interacts with titanium oxide, iron, and other metals to produce a constantly evolving chemical soup. This may generate reactive compounds, charged particles, and localized plasma discharges, all of which feed back into the extreme winds and metallic precipitation. The atmosphere is not static. It is a living, dynamic system of fire, metal, and chemical energy operating on scales that dwarf terrestrial storms or weather patterns. Every breath of air, or rather any attempt to breathe, would be instantly lethal. A mixture of vaporized metals, corrosive compounds, and ionized particles. The hostile chemistry also contributes to the planet's energy distribution. Titanium oxide and similar compounds selectively absorb radiation, concentrating energy in certain regions while leaving others relatively cooler. Combined with the tidal locking, this creates a world where one side is a furnace and the other a frigid, storm-ridden wasteland, with violent gradients along the terminator line producing the most intense, dynamic storms imaginable. This is a planet where atmospheric physics operate at their limits, a realm where chemical composition dictates the flow of energy, the intensity of storms, and the very nature of its weather systems. For astronomers, the presence of titanium oxide and other exotic chemicals provides crucial insights. By analyzing the planet's spectral signatures, scientists can detect the composition, temperature, and even the circulation patterns of the atmosphere. These measurements reveal a planet with a sky unlike any other, chemically reactive, molten metal-laden, and dynamically unstable. Each discovery reinforces the understanding that this is not a mere gas giant or a hot Jupiter in the conventional sense, but a living laboratory of extreme physics where the very air is hostile, chemically charged, and actively shaping the planet's violent environment. Ultimately, the exotic atmosphere of this planet cements its status as one of the most horrifying worlds ever discovered. It is not just hot, not just windy, and not just raining molten metal. It is chemically active, radiatively intense, and dynamically chaotic. The presence of titanium oxide and other exotic compounds ensures that every gust of wind, every storm, and every metallic rain event is amplified, creating a planet-wide system of destruction. The skies are alive with energy, chemical interactions, and radiant fury. A hostile environment that reinforces the terrifying reality of this alien world. The air itself is a weapon, the clouds a furnace, and the chemical composition a reminder that in this corner of the cosmos, nothing is gentle, safe, or familiar. The immense gravitational pull of the nearby star does more than just scorch this planet with relentless heat. It physically contorts it. Orbiting so closely, the planet experiences tidal forces of staggering intensity, strong enough to stretch its mass into an elongated oval shape. Unlike Earth, or even Jupiter, which are nearly spherical, this planet is pulled along the axis pointing toward its star, creating a form that seems almost unnatural, a distorted world shaped by the very forces that define its extreme environment. This deformation is not merely a geometric curiosity, it has profound consequences for everything else happening on the planet, from atmospheric dynamics to wind patterns, storm formation, and even the behavior of molten metals raining from the skies. The planet is, in effect, trapped in a gravitational vice, twisted by the star's relentless pull. This distortion enhances the severity of the planet's extreme conditions. Because it is elongated, the surface gravity is uneven, stronger along the stretched axis and weaker toward the poles. This imbalance influences how the dense metallic atmosphere circulates, driving supersonic winds in unpredictable patterns and concentrating storms in certain regions. The oval shape also affects how heat is distributed. The side of the planet facing the star receives the full brunt of radiation, and the shape exaggerates the gradient between the day and night sides. Atmospheric circulation must compensate for both tidal distortion and tidal locking simultaneously, resulting in chaotic weather systems that are far more extreme than they would be on a spherical planet. Every gust of wind, every storm of molten metals, and every swirl of vaporized clouds is intensified by the planet's warped shape. From a visual perspective, the elongation gives the planet an eerie, alien appearance, even from light years away. It is no longer a simple sphere orbiting a star, but a warped, oblong figure that appears almost like a planet in torment, twisted by forces far beyond human comprehension. Telescopic observations reveal subtle asymmetries in light and shadow, with the extended sides reflecting and scattering the star's intense radiation differently than the compressed regions. This contributes to the planet's spectral signature, giving astronomers insight into its extreme atmospheric and gravitational interactions. The oval shape itself becomes a marker of the immense physical stress the planet is under, a visible testament to the violent forces at play. The tidal deformation also has consequences for the planet's internal structure. The immense gravitational pull stretches the interior, potentially affecting its core and mantle in ways that Earth-based geology cannot replicate. Internal friction from this continuous stretching could generate additional heat, contributing to the already extreme surface temperatures and driving even more violent atmospheric convection. In other words, the planet's warped shape does not merely distort its exterior, it feeds back into its internal energy, creating a cycle of heating, wind, and storm formation that is self-reinforcing. The result is a planet that is literally contorted by its star, an unyielding furnace both inside and out. The combination of tidal locking and tidal stretching produces a planet that is fundamentally alien. Unlike any world familiar to us, it has no symmetry, no equilibrium, and no areas of stability. Its shape, coupled with supersonic winds, molten metal rain, and an exotic chemical atmosphere, ensures that every square kilometer is defined by extremes. The distorted oval form amplifies the horror of the environment, making the storms more chaotic, the precipitation more violent, and the temperature gradients even more lethal. The planet is not just inhospitable, it is a physical embodiment of cosmic violence, where the star's gravity has reshaped matter itself into a form that serves the relentless fury of extreme physics. From a scientific perspective, this distortion provides invaluable insight into the mechanics of tidal forces and planetary deformation. By analyzing how the planet's shape responds to its star, astronomers can study the interactions between gravity, rotation, and atmospheric dynamics under conditions far beyond those seen in our solar system. The elongated form helps explain the distribution of storms, winds, and metallic clouds, offering a rare glimpse into the physics of planets under extreme tidal stress. Observing such a warped giant allows scientists to refine models of planetary structure, evolution, and atmospheric behavior in a regime that pushes the boundaries of known physics. Ultimately, the distorted shape of this planet adds a new dimension to its terror. It is not merely a hellish environment because of heat, wind, or molten metals. It is a world whose very geometry has been twisted by the star it orbits. Every storm, every wind gust, every metallic downpour is influenced by this unnatural form. It stands as a stark reminder that the cosmos is not gentle or orderly. It is capable of reshaping worlds, bending matter, and creating environments of unimaginable extremes. This planet is more than just a hot Jupiter. It is a contorted, living testament to the violent, unpredictable, and horrifying possibilities that exist beyond the safety of Earth. Planets like this one fall into a category astronomers call hot Jupiters, a term that immediately conveys both their immense size and their extraordinary proximity to their parent stars. Hot Jupiters are gas giants, comparable in scale to Jupiter or Saturn, but orbiting far closer to their stars than Mercury does to our Sun. Unlike the gas giants of our solar system, which dwell in the frigid outer reaches, these planets endure unrelenting stellar radiation, extreme heat, and intense gravitational forces. Their proximity often leads to tidal locking, extreme atmospheric dynamics, and other phenomena that transform them into worlds that challenge every expectation we have of planetary behavior. In essence, hot Jupiters are Jupiter-like giants, but subjected to conditions so extreme that the very nature of their atmospheres, winds, and weather systems is radically altered. What sets this planet apart from other hot Jupiters is the extremity of every factor that defines the category. Many hot Jupiters already endure temperatures of thousands of degrees Celsius, orbit very close to their stars, and experience high-speed winds. But this planet pushes all of those characteristics to their limits. It orbits so close that a year lasts barely 2.7 Earth days. Its dayside is heated to over 3,200 degrees Celsius, and supersonic winds transport vaporized metals across its massive, oval-shaped body. The combination of metallic clouds, molten precipitation, extreme chemical composition, tidal stretching, and unrelenting stellar radiation places this world far beyond the typical hot Jupiter into a realm of planetary extremity that is almost unimaginable. While other hot Jupiters are already hostile, this planet exemplifies the upper bound of what is possible for such worlds, making it an extraordinary case study for astronomers and a terrifying object in the cosmic landscape. One of the defining characteristics of hot Jupiters is their close-in orbits, which cause them to be intensely irradiated and tidally locked. On many such planets, this leads to a permanent day side and a permanent night side, creating extreme thermal gradients that drive winds and atmospheric circulation. On this planet, those principles are magnified. The day side is a furnace that vaporizes metals, while the night side is relatively cooler, but still suffused with supersonic winds, metallic precipitation, and chaotic storm systems. The tidal stretching caused by the star's gravity is also more pronounced than on most hot Jupiters, further exaggerating wind patterns and storm intensity. In other words, every atmospheric and structural feature that defines a hot Jupiter is present here, but on a scale and intensity that elevate the planet from extreme to nightmarish. In addition to its proximity and orbital period, the chemical and physical extremes of the atmosphere contribute to its distinction. Most hot Jupiters have atmospheres dominated by hydrogen and helium, with some containing clouds of silicates or other compounds. This planet, however, has an atmosphere rich in exotic metals like iron and titanium, as well as titanium oxide, which blocks and redistributes heat in ways far beyond anything seen on typical hot Jupiters. The vaporized metals condense into molten precipitation. Supersonic winds carry them across thousands of kilometers, and the elongated oval shape of the planet amplifies all of these effects. In effect, the planet takes the baseline characteristics of hot Jupiters and magnifies them into a full-scale planetary inferno. A world where every defining trait of the category is turned into an extreme hazard. From an observational perspective, this planet is also remarkable among hot Jupiters because of its atmospheric signature. Astronomers have been able to directly study its light, revealing the metallic composition and even the eerie blue glow caused by scattering in its upper atmosphere. While many hot Jupiters are too faint or too distant to allow such detailed characterization, the intensity of this planet's star, combined with its massive size and highly reflective metallic clouds, allows for detailed spectroscopic analysis. This provides not only confirmation of its status as an extreme hot Jupiter, but also a rare glimpse into how physics operates under conditions of extreme temperature, gravity, and chemical complexity, an opportunity that few other planets of this type afford. In essence, this planet exemplifies the hot Jupiter category, while simultaneously redefining its limits. It is a gas giant in scale, a furnace in heat, a tempest in its storms, and a chemical laboratory in its atmosphere. Everything that makes hot Jupiters interesting and terrifying is amplified here. Its proximity to its star, massive size, tidal deformation, supersonic winds, molten metal rain, and exotic chemical atmosphere converge to create a world that pushes the concept of hot Jupiter into realms that are almost science fictional, yet entirely real. It is a vivid demonstration of how extreme planetary physics can become when the universe combines size, proximity, and stellar energy into a single, horrifying entity. The true horror of this planet emerges when considering what it would mean to experience it up close, or even remotely. There is no solid ground, no stable surface upon which to stand or survive. The entire world is a roiling expanse of gas, vaporized metals, and chemically charged clouds. Temperatures soar to levels that would instantly incinerate any known form of life, while supersonic winds and molten metal rain ensure that no region is ever calm or safe. Unlike rocky planets where certain regions may offer shelter from storms or heat, this planet offers no sanctuary. Its entire atmosphere is a furnace, every square kilometer a region of perpetual violence and extreme energy. To put it bluntly, this is a world that defies the very concept of habitability. Life as we understand it could not possibly exist here, and any probe or craft venturing into its environment would be obliterated almost immediately. The combination of extreme heat, supersonic winds, metallic precipitation, and exotic chemical composition creates an environment that is fundamentally alien. On Earth, storms, hurricanes, or lightning may be destructive, but they are transient, localized, and relatively survivable with proper protection. On this planet, there is no such reprieve. The day side is a furnace hotter than many stars, vaporizing metals into the atmosphere, while the night side is still far hotter than any desert or volcanic region on Earth. Supersonic winds tear across the globe, transporting molten metals across thousands of kilometers, creating a perpetual cycle of violent storms. Even the act of falling metal droplets carries unimaginable energy, enough to disintegrate any material they strike. The planet is, in every sense, an environment of unrelenting, inescapable danger. Its terrifying nature is compounded by the distorted, oval shape, which magnifies the chaos of its atmospheric systems. Tidal forces stretch the planet, creating uneven gravity that affects every process from storm formation to wind circulation. The molten metal rain does not fall evenly. It is channeled and enhanced by gravitational irregularities, further intensifying the violence of the weather. Atmospheric chemistry, rich in titanium oxide and other exotic compounds, creates a sky that is not merely visually alien, but physically hostile. In combination, these features ensure that the planet is not just hot or stormy, but fundamentally and comprehensively inhospitable. It is a world where every environmental factor conspires against the possibility of life or stability. Even visually, the planet inspires a sense of dread. The eerie blue glow caused by atmospheric scattering, the metallic clouds reflecting light in strange spectral patterns, and the molten rain streaking across the skies create a scene that is simultaneously mesmerizing and apocalyptic. From a distance, it may appear as a haunting alien jewel in the cosmos, but this beauty is an illusion. Up close, the environment is entirely lethal. It serves as a chilling reminder that the universe is capable of creating conditions so extreme that even the most basic expectations of survivability, stability, and habitability are completely inverted. From a scientific standpoint, its horrifying nature is also why this planet is of such interest. Studying a world where life cannot exist, where temperatures rival stars, and where atmospheric physics operate at extremes, provides insight into the limits of planetary formation, the behavior of exotic materials, and the dynamics of tidal interactions. Its extreme environment is a natural laboratory, one that allows scientists to observe phenomena that cannot be reproduced on Earth. Yet the same factors that make it scientifically fascinating are precisely what make it terrifying. It is a vivid, physical manifestation of how violent and uninhabitable planets can be in our galaxy. The horror of this planet is not just its heat, storms, or metallic precipitation. It is the realization that the universe can produce worlds so extreme, so fundamentally alien, that everything familiar about planets is inverted. There is no solid ground, no breathable atmosphere, no water, and no respite from the relentless heat and storms. The planet exists in a state of perpetual violence, a massive, distorted inferno of molten metals, supersonic winds, and chemically charged skies under a star that never sets on the dayside. It is a world that humbles human imagination, where even the most basic notions of habitability, stability, and survival are obliterated. This is a world that exists purely in extremes, a cosmic furnace that reminds us of the terrifying possibilities that lie beyond the safe confines of our solar system. Beyond its terrifying physical characteristics, this planet captivates astronomers because of the way it interacts with light. Unlike most distant exoplanets, which are too faint or too small to be observed in detail, this world emits and reflects a sufficient amount of light to allow direct study of its atmosphere. Using sophisticated spectroscopic instruments, scientists have been able to analyze the light coming from the planet, detecting specific signatures that reveal its composition and the peculiar behavior of its atmosphere. The eerie glow, an almost spectral blue caused by the scattering of stellar light through vaporized metals and exotic chemicals like titanium oxide, offers a glimpse into a world that is simultaneously alien and extreme. The ability to measure these signatures directly is a rare achievement in exoplanetary science, made possible by the planet's size, proximity to its star, and highly reflective, metal-rich clouds. This glow is more than just visually striking. It provides essential data about the dynamics of the planet's atmosphere. By observing the intensity and wavelength distribution of the light, astronomers can infer the presence of vaporized metals, track temperature variations across the day and night sides, and even estimate wind speeds based on Doppler shifts in the spectral lines. The glow essentially acts as a fingerprint, revealing the complex interplay of heat, chemical reactions, and atmospheric circulation that defines this planet's extreme environment. In other words, the light emitted and reflected by the planet is both a window and a warning. It allows scientists to study conditions that would be fatal for any human, while simultaneously hinting at the violent processes occurring across its massive surface. Moreover, the spectral signature confirms many of the planet's most extreme properties. The presence of vaporized iron and titanium, the unusually high temperatures, and the reflective clouds of exotic compounds all contribute to the distinctive hue seen from afar. By analyzing subtle shifts in the glow as the planet orbits its star, astronomers can map temperature gradients, atmospheric composition, and even storm activity, essentially observing a continuously raging inferno hundreds of light years away. This level of direct observation is extraordinarily rare in exoplanetary studies. Most known exoplanets are detected indirectly through transits or gravitational effects. The fact that this planet's light can be resolved in such detail makes it an exceptional subject for understanding not only hot Jupiters, but also the limits of planetary physics under extreme conditions. The glow also reinforces the haunting alien character of the planet. From a distance, it appears almost like a jewel suspended in the void, its spectral blue a stark contrast to the darkness of space. Yet this beauty is deceptive. The radiance comes from the interaction of intense heat, vaporized metals, and exotic atmospheric chemistry. The same processes that create a mesmerizing visual effect are responsible for storms of molten metal, supersonic winds, and atmospheric instability. Observing the glow, scientists, and anyone imagining the scene, are reminded that the planet's exterior brilliance belies a deeply hostile and dynamic environment. The blue light is not a signal of life or calm, but a warning of the extreme physics at play. Studying this glow also has profound implications for our understanding of planetary formation and atmospheric science. By comparing the light signatures with theoretical models, scientists can refine predictions about how such extreme hot Jupiters evolve, how they redistribute heat across tidally locked surfaces, and how exotic chemical compositions affect radiative balance. Each photon captured from this distant world is effectively a data point, helping us understand the physics of atmospheres that exist at the boundary between planets and stars. It is both a practical tool for scientific inquiry and a stark illustration of the planet's terrifying uniqueness. Ultimately, the glow in space is one of the few ways humanity can observe and connect with this alien inferno. It serves as a beacon in the darkness, a visual manifestation of everything that makes the planet horrifying and fascinating. Extreme heat, metallic storms, supersonic winds, exotic chemistry, and an environment utterly inhospitable to life. Through the study of its light, astronomers are able to peer into the inner workings of a world that exists as a reminder of the cosmic extremes that lie beyond the familiar calm of our solar system. This planet, observed through its eerie glow, stands as both a scientific marvel and a symbol of the universe's capacity for creating environments so alien and violent that they challenge the limits of imagination. This planet challenges our very understanding of what a planet is. In nearly every respect, it behaves more like a star than a typical gas giant, a testament to the extreme energy and heat it absorbs from its nearby star. The day side, perpetually facing the scorching stellar furnace, reaches temperatures of roughly 3,200 degrees Celsius, which is hotter than some smaller stars and comparable to the surface of K-type stars. This level of heat is sufficient to vaporize metals, drive supersonic winds, and sustain clouds of molten iron and titanium that rain down continuously across the planet's vast, distorted surface. In effect, it functions like a miniature star with its own self-sustaining atmosphere of radiant energy and flowing molten material. Unlike a star, however, it lacks the nuclear fusion at its core that powers stellar objects, but the visual and thermal impact is eerily similar. A body of incandescent material radiating enormous amounts of energy, glowing in spectral patterns that blur the boundary between planet and failed star. Astronomers have long categorized planets and stars based on size, composition, and energy generation. But this world exists in the uncomfortable grey area between these definitions. Its enormous size, 1.6 times the radius of Jupiter, and thick, metal-rich atmosphere allow it to absorb and redistribute extraordinary amounts of stellar energy. Titanium oxide in the atmosphere functions like an extreme reflective blanket, trapping heat and creating thermal gradients that rival the convection processes in small stars. Meanwhile, the supersonic winds and metallic clouds act like plasma flows in stellar coronae, moving energy across the planet in a way that resembles stellar dynamics on a planetary scale. Observing this planet, one could almost imagine it as a failed star that never ignited nuclear fusion, but nonetheless mimics a star's radiant and violent energy output through the relentless heating and circulation of its atmosphere. Its identity as a planet seems almost inadequate, as though the term cannot fully capture the scale, intensity, and energy flows present within this extreme world. The star-like qualities extend beyond its radiant energy to the way it interacts with its parent star and its orbital environment. Orbiting extremely close to a massive A-type star, this planet intercepts enormous amounts of radiation, much more than Jupiter or Saturn would ever experience in our solar system. The tidal forces exerted by the star, combined with its proximity and distorted oval shape, create conditions where gravitational energy further heats the interior and atmospheric layers. In effect, the planet is not a passive receiver of stellar energy. It actively redistributes and re-radiates it in ways that mimic the thermodynamic processes of a low-mass star. Even its outer layers of vaporized metals and exotic compounds participate in this radiative feedback loop, reflecting and scattering light across the globe in patterns that are simultaneously mesmerizing and terrifying. Viewed from afar, the planet's glow and spectral signature are so pronounced that one could mistake it for a diminutive star, a glowing ember in the vast darkness of space. This star-like behavior also has profound implications for its atmosphere and weather systems. On Earth, or a typical gas giant, heating occurs largely through solar radiation absorption. But this planet operates at an intensity that transforms ordinary physical processes into extreme phenomena. Atmospheric convection is no longer a gentle vertical movement of gases. It becomes a violent, global-scale flow of ionized metals and chemically reactive gases. Supersonic winds, fueled by the immense day-night temperature gradients, sweep molten metals across thousands of kilometers, forming sheets of vaporized elements that condense into fiery precipitation. The metallic clouds act almost like plasma streams, conducting heat and energy across the distorted, oval-shaped body. Every component of the planet, from its upper atmosphere to its interior layers, participates in this star-like energy system, a continuous flow of radiative and kinetic energy that defies terrestrial comparisons. The thermal emissions of the planet contribute to its classification as a star-like world. Unlike most exoplanets, which remain invisible to direct observation due to faint reflected light or infrared emissions, this planet radiates enough heat to be detected directly using sophisticated infrared instruments. The energy it emits is extraordinary, not merely reflective of the stellar light it absorbs, but amplified by its enormous size and chemical composition. Clouds of titanium oxide and vaporized metals scatter this radiation in complex ways, creating a spectral signature that combines aspects of planetary atmospheres with characteristics of stellar bodies. Astronomers can study this signature to measure wind speeds, temperature distributions, and even the composition of vaporized metals, a feat rarely possible with any exoplanet. In effect, the planet itself behaves as a mini laboratory for stellar physics, a star-like object without nuclear fusion, glowing and radiating energy in ways that challenge the strict categories of planet versus star. In addition to the physical and observational aspects, the star-like qualities of the planet also extend to its visual impact across the cosmos. The eerie blue glow observed from Earth, created by scattering from metal-rich clouds and atmospheric chemicals, is intensified by the planet's enormous size and reflective properties. From a distance, it appears as a radiant, spectral object hovering near its parent star, resembling a small star more than a typical gas giant. The distorted oval shape amplifies the intensity of light along certain axes, producing asymmetrical radiance that flickers subtly as the planet rotates and the supersonic winds shift metallic clouds. This is not merely a point of light in the sky. It is a dynamic, glowing object that conveys the ferocity of its environment through both color and intensity, a planet masquerading as a star in the theater of the cosmos. The star-like behavior also informs how scientists model its interior and structure. While planets and stars are fundamentally different, this planet challenges that distinction by operating near the limits of both categories. Its internal heat distribution, tidal deformation, and atmospheric dynamics are more reminiscent of a small star's convective processes than a conventional gas giant. The planet's core, likely compressed and heated by both gravity and tidal forces, radiates energy that drives atmospheric circulation in a feedback loop, amplifying storms, wind speeds, and metallic precipitation. This continuous exchange of energy blurs the lines between planetary and stellar physics, creating a hybrid system in which the planet functions as both a giant gaseous body and a quasi-stellar energy emitter. In this sense, it is not merely a planet orbiting a star, it is a star-like object defined by its extreme environment, dynamic energy flows, and radiant output. The conceptual horror of this classification cannot be overstated. By behaving more like a failed star than a conventional planet, it forces us to reconsider our understanding of planetary formation, atmospheric dynamics, and the limits of celestial classification. It is a reminder that the universe is capable of producing objects that defy neat categories, where a planet can glow, radiate, and behave in ways that are indistinguishable from a star at first glance. This uncertainty only deepens the sense of dread. It is a world so extreme, so alien, that the very definitions we rely on to understand celestial objects fail. The planet exists in a liminal space between the known and the unknowable, a tangible illustration of how violent, radiant, and uninhabitable the universe can be. Studying this planet provides a window into the extreme boundaries of planetary physics, allowing scientists to explore processes that cannot be reproduced or observed within our solar system. Its extreme proximity to a massive, scorching star, combined with its enormous size, distorted oval shape, and supersonic metallic winds, creates an unparalleled natural laboratory. By observing the planet, astronomers can examine the physics of tidally locked worlds, where one side experiences perpetual daylight and the other is trapped in eternal night. These observations help refine our understanding of heat redistribution across atmospheres under extreme irradiation. The interplay of radiation, tidal forces, and atmospheric dynamics on this planet serves as a high-intensity test case for models that attempt to predict weather patterns, storm formation, and energy transport in exoplanetary atmospheres. Every storm, every metallic rain event, and every chemical reaction occurring on the planet offers critical insights into how gases and metals behave when subjected to forces and temperatures far beyond terrestrial conditions. The study of this planet also advances our knowledge of planetary formation and evolution. Hot Jupiters challenge traditional theories because gas giants are generally expected to form in the colder, outer regions of star systems and migrate inward over time. Observing a planet like this, so close to its star and already demonstrating extreme atmospheric phenomena, helps scientists understand the mechanisms of planetary migration. How does a massive gas giant survive such a close orbit without disintegrating? How do tidal forces, radiation pressure, and atmospheric erosion interact over billions of years to shape its current state? The combination of spectral data, thermal measurements, and orbital dynamics allows researchers to piece together its history, providing clues about the evolution of planetary systems under extreme conditions. In this way, the planet functions as both a subject of study and a case study in the limits of planetary endurance. Atmospheric chemistry is another area where the planet provides invaluable scientific insights. Its skies contain exotic compounds such as titanium oxide, vaporized iron, and other metals that behave radically differently under intense heat and radiation than they would under more temperate conditions. By analyzing these chemical signatures through spectroscopy, astronomers can determine how these substances interact, condense, and circulate in a planet-wide system. These observations are crucial for understanding how extreme atmospheres operate, not only for hot Jupiters, but also for other exoplanets that may experience intense stellar irradiation. Moreover, The presence of vaporized metals and molten precipitation offers a natural laboratory for studying phase changes, cloud formation, and chemical transport under conditions of extreme gravity, wind speeds, and temperature gradients. The findings here have implications that extend beyond this single planet, informing models of atmospheric physics across a wide range of stellar and planetary environments. Observations of the planet's distorted shape and tidal deformation further enrich our understanding of planetary structure and dynamics. The elongation caused by the star's gravitational pull demonstrates the real-world impact of tidal forces on massive gas giants. By studying how the atmosphere and internal layers respond to this extreme stretching, scientists can refine models of planetary interiors, gravitational stress, and energy distribution. These insights are applicable not only to hot Jupiters, but also to moons, binary planets, and other celestial bodies that experience intense tidal interactions. Essentially, this planet allows us to observe, in real time, how matter behaves under the extreme combination of gravity, heat, and rotation, conditions that are otherwise impossible to reproduce in laboratories on Earth. The planet's radiant glow and directly observable spectral signatures offer another dimension of study that is rarely possible for exoplanets. Direct observation of emitted and reflected light allows astronomers to map temperature distributions, detect chemical compositions, and measure wind speeds across different regions. These measurements can validate and refine computer models that simulate extreme exoplanetary atmospheres. By comparing real observational data with theoretical predictions, scientists can identify discrepancies, adjust assumptions about heat transport, chemical interactions, and cloud formation, and ultimately improve our understanding of planetary physics under extreme conditions. It also allows researchers to calibrate methods for studying more distant or fainter exoplanets, expanding the reach of exoplanetary science across the galaxy. Studying this planet also informs our understanding of energy transfer and chemical processes in high radiation environments. Titanium oxide and vaporized metals in the atmosphere absorb, scatter, and redistribute stellar radiation in ways that mirror, yet greatly exceed, processes seen on Earth or within our solar system's gas giants. Observing these interactions helps scientists explore how energy is moved through extreme atmospheres, how chemical compounds react under extreme irradiation, and how violent weather systems can form and sustain themselves. In effect, the planet becomes a natural experiment in thermodynamics, fluid dynamics, and chemistry under conditions far beyond human-engineered experiments, providing insights that would otherwise remain theoretical. From a broader perspective, studying this planet also allows us to explore the outer limits of habitability and planetary diversity. While it is unequivocally uninhabitable, understanding why and how such extreme worlds form, survive, and evolve helps contextualize the search for more temperate, potentially life-supporting planets. By mapping the extremes, scientists can refine criteria for planetary stability, atmospheric retention, and thermal balance, which in turn informs models of planetary systems where life might exist. The study of inhospitable extremes provides a necessary counterpoint to the search for habitable worlds, offering a more complete understanding of the diversity and complexity of planets across the galaxy. The study of this planet exemplifies the synergy between observation and theory in modern astronomy. Using a combination of telescopes, spectroscopic instruments, and computational models, scientists can observe this planet's glow, measure wind speeds, identify chemical compositions, and reconstruct its orbital dynamics. Each dataset contributes to a growing understanding of planetary physics under extreme conditions, enabling researchers to make predictions about other hot Jupiters and even more exotic exoplanets. The insights gained here will resonate across astrophysics, planetary science, and atmospheric chemistry, providing knowledge that extends far beyond this one extraordinary world. This planet stands as a stark reminder of the universe's capacity for violence and extremes, a cosmic warning of what lies beyond the relative safety of Earth. From the comfort of our home planet, it is easy to assume that planets are relatively benign environments, rocky surfaces, temperate climates, and atmospheres that sustain life. Yet the reality is far more terrifying. This world demonstrates that planets can exist in states of near-constant chaos, shaped by forces so intense that they challenge our understanding of physics, chemistry, and atmospheric dynamics. Its extreme heat, supersonic winds, molten metal rain, distorted shape, and star-like radiance all serve as proof that the cosmos is not a gentle or orderly place. The universe is capable of producing worlds that are utterly inhospitable, objects where every factor conspires against life, stability, and predictability. The cosmic warning is not just about extreme heat or alien chemical compositions. It is about the sheer unpredictability of conditions that can arise naturally. Tidal forces stretch the planet into an oval, atmospheric circulation moves molten metals at supersonic speeds, and exotic chemical clouds redistribute heat in ways that defy terrestrial analogues. The universe has no obligation to create planets that are hospitable, stable, or comprehensible. This planet is living proof that the laws of nature, while consistent, can produce outcomes that are shocking, violent, and wholly alien. It exists as a giant furnace, a distorted oval, a rain of molten metals, and a high-speed wind machine all at once. A world where the extremes we can imagine on Earth are trivialized by the sheer scale and intensity of natural forces. Moreover, its proximity to a massive, scorching hot star magnifies every potential hazard. The star's radiation does more than warm the planet. It drives chemical reactions in the atmosphere, sustains vaporized metals, and fuels supersonic winds that circle the globe. The planet's oval shape, created by tidal stretching, intensifies this chaos by creating uneven gravity, which channels storms and molten precipitation into unpredictable patterns. Observing these phenomena from afar, scientists are reminded that our solar system is unusually stable and temperate. Earth, with its moderate temperatures, protective magnetic field, and relatively placid star, is an exception rather than the rule. This planet is the cosmic counterpoint, a vivid example of how extreme and inhospitable the universe can be. The warning also extends to the fragility of planetary environments in general. Planets are not inherently stable. Their survival and composition depend on delicate balances of gravity, radiation, chemical composition, and orbital mechanics. When any of these factors reach extremes, the planet transforms into something almost unrecognizable. This world's extreme irradiation, tidal deformation, molten precipitation, and metallic winds illustrate what can happen when planetary systems operate at the limits of stability. It is a reminder that Earth's hospitable conditions are both fragile and exceptional, and that the cosmos as a whole contains countless environments that would instantly obliterate any terrestrial life. From a scientific perspective, this cosmic warning is also a motivation for exploration and study. By observing such extreme planets, astronomers gain a clearer sense of the range of planetary diversity and the boundaries of habitability. It provides a natural laboratory for understanding how energy, matter, and chemical processes behave under extreme conditions, while simultaneously offering a sobering perspective on how violent and inhospitable the universe can be. Each observation of the planet's glow, each measurement of supersonic winds or metallic clouds, reinforces the message. The cosmos is not inherently friendly, and even within relatively ordinary star systems, extraordinary extremes can exist. There is also a philosophical dimension to this warning. while humanity often imagines the universe as a vast but comprehensible place. This planet illustrates that the cosmos operates on scales and in ways that can be utterly alien. The universe does not prioritize habitability or safety. It produces extremes that defy human intuition. The incandescent glow, molten metal storms, supersonic winds, and distorted geometry of this planet are a testament to the indifferent power of natural laws. They demonstrate that life-friendly environments like Earth are rare islands in a vast ocean of cosmic hostility, and that the extremes found elsewhere are far more common than the temperate conditions we take for granted. Finally, this cosmic warning is not merely theoretical, it is directly observable. Telescopes and spectroscopic instruments allow scientists to detect the planet's light, map its chemical composition, and measure its extreme temperature and atmospheric dynamics. These observations turn an abstract concept, the danger and extremity of the universe, into a tangible reality. The glowing blue spectral signature, the evidence of molten metal rain, and the supersonic atmospheric winds all serve as a visceral reminder that the universe contains worlds of unimaginable intensity and hostility. It is a warning not only to scientists, but to all who consider the vastness of space. The cosmos is capable of producing phenomena far beyond our imagination, and Earth is a rare haven amidst a universe defined by extremes. As we bring this journey through the horrors of the cosmos to a close, the reality of this planet leaves a lingering, chilling impression. Every aspect of its existence, the star-like glow, the molten metal rain, the supersonic winds, the blistering temperatures, and the distorted oval shape, paints a portrait of a world that is incomprehensibly hostile. Unlike the worlds imagined in science fiction, this is not a fictional construct designed to thrill or terrify. It is a tangible, observable planet drifting hundreds of light years away in the constellation Libra, and its extremity dwarfs even the wildest fantasies of interstellar apocalypse. The thought that such a place exists in the same galaxy that harbors our Earth underscores the stark contrast between the placid, life-supporting environment we inhabit and the universe's capacity for violent, uninhabitable extremes. The closing reflection must also grapple with the terrifying scale of forces at play. This planet endures constant exposure to a massive, scorching hot star, its surface temperatures hotter than some stars themselves. Supersonic winds sweep across the globe at thousands of kilometers per hour, carrying clouds of vaporized iron and titanium, which then condense into fiery precipitation, relentlessly bombarding the already searing atmosphere. Tidal forces stretch the planet into an unnatural oval, enhancing storms and amplifying the chaotic redistribution of heat and energy. Its distorted shape, its blinding eerie blue glow, and the sheer intensity of its environment combine to create a world that seems almost sentient in its hostility, a natural inferno where nothing familiar to human experience could survive. The sheer scale and intensity of these phenomena are humbling reminders of how indifferent and extreme the universe can be. From a scientific standpoint, the planet continues to captivate because it challenges conventional definitions and models. As a hot Jupiter, it exists in a category of exoplanets already considered extreme, yet it stands out as one of the most extraordinary examples. Its combination of extreme heat, atmospheric complexity, metallic clouds, and direct observability provides an unprecedented laboratory for understanding the limits of planetary formation, atmospheric physics, and orbital dynamics. Every measurement of its light, every spectral analysis revealing titanium oxide or vaporized metals, every observation of its supersonic winds or thermal gradients contributes to our understanding of how planets can behave when pushed to the brink of physical extremes. Yet even in the midst of this scientific fascination, the underlying reality remains terrifying. This is a place utterly inhospitable, a world of relentless fury that exists simply because the laws of nature allow it. Perhaps the most haunting aspect of this planet is the scale of its alienness. From Earth, we can detect its glow and measure its atmospheric components, yet these observations only hint at the true ferocity of its environment. Imagining standing on its surface, or what could be considered a surface in a distorted, molten metal cloudscape, is almost impossible. There is no solid ground, no respite from heat, no moments of calm. Every aspect of its physical state, temperature, winds, chemical composition, tidal distortion, is designed not for life, not for stability, but for extremes. It serves as a stark reminder that planetary environments across the universe need not resemble anything we consider normal or safe. While we often anthropomorphize planets in our imagination, picturing them as places that could host life or resemble our own solar system, this planet obliterates those assumptions entirely. In a broader cosmic perspective, this planet exemplifies the universe's capacity for the extraordinary and the terrifying. The contrast between Earth, a planet teeming with life, protected by a moderate atmosphere, a magnetic field, and a star that provides energy at just the right intensity, and this hellish exoplanet is staggering. It highlights the rare conditions that allow life to exist and emphasizes how commonplace extremes might be in the galaxy. For every temperate, habitable planet, there may be dozens, hundreds, or thousands of worlds operating under conditions that defy human comprehension. Planets of fire, metal, and eternal storms, where the very laws of physics manifest in forms that are both mesmerizing and horrifying. Observing this world, humanity is confronted with the fact that the universe is not designed with life in mind. It is a vast, indifferent expanse where extremes can and do manifest in ways that stretch the imagination. Finally, the most chilling realization is that this planet is not a theoretical object or a product of artistic speculation. It is real. It exists in a galaxy filled with stars, planets, and possibilities, drifting silently but violently, hundreds of light years away from Earth. It is a planet where metals rain from the sky, where one hemisphere is trapped in eternal daylight and the other in endless night, where supersonic winds sweep molten clouds across a distorted surface, and where the glow of the atmosphere blurs the line between planet and failed star. It is a living testament to the extremes that nature can produce, and a vivid reminder that the universe is far stranger, more violent, and more alien than our imaginations can easily grasp. In the cosmic theatre, Earth is a calm stage, while this planet is a blazing inferno, a relentless reminder that the universe operates on scales and in conditions that are profoundly indifferent to life, safety, or habitability. WASP 189b is not science fiction. It is real. A world of fire, metal, eternal storms, and radiant fury, drifting far beyond our reach, a terrifying testament to the extremes of the cosmos and the violent potential inherent in planets that exist outside the protective bubble of habitability. It is a planet that challenges everything we think we know about planetary environments, a cosmic warning, a scientific marvel, and an unrelenting inferno all at once. A place where the word planet barely captures the hostile reality of its existence. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.